All right, this video is about how to calculate the pH for a titration of a weak acid with a strong base. So let's kind of go through the overall process we talked about in class today. So the first thing we have to do is realize that once we've added base to that weak acid, we've created a buffer. And so we have a common ion problem because you will have in solution the weak acid and its conjugate base. And so that's going to not make our calculations harder, just longer. It's not going to be as easy as a strong acid. Okay. So what we have to do first on any problem, this is weak acid, strong base, or any titration really, is you've got to let the acid and base react. So on our strong, we did this step. So let the acid and the base react and classify what's left in the beaker. I call them the leftovers. So to do this, you need to set up your mole table. So I expect to see a mole table. AP expects to see a mole table. Now, if you don't like calling it an ice table because that confuses you with equilibrium, call it an ICF table. And I still initial moles. C will be the change in moles from the limiting based on the limiting reactant. And then F will be final. What do you have after the reaction is complete? Because this is not equilibrium, right? This is a chemical reaction. So we assume it goes to completion. Um, so I'm going to do ICF today. We did ICE in class, but I'll do ICF. All right, the second step, now that you have your leftovers, if your leftovers, so I'm talking in terms of the weak acid, strong base, if you're going to use your FRO of your ICF table, your mole table, your stoichiometry table, if you have oh, sorry. Step two, I say get the concentrations based on the FRO. So that makes sense. Because you're going to, if you end up with equilibrium or not, you're still going to need the concentration before you can get a pH. So use the FRO from step one. That'll be your moles or your millimoles and divide by the volume, either in liters or milliliters. I work in millimoles, so I'm going to take millimoles divided by milliliters. If you work in moles, then you'll take moles divided by liters. And this will be total volume of the acid you started with plus the volume of the base you added. So this is a combined volume. All right, the total volume. Once you've got your new concentrations, then comes the work. So if the contents, if you haven't added any base, then all you have is the weak acid. You do the equilibrium table, you get pH the way we did on the last test. Once you've started adding base, though, you're now, the contents are going to be, as long as the base is limiting, you're going to be left over with the weak acid and its conjugate base. Of course, water's in all of this. We don't care about the water. Just put it there, but we don't include it in our net ionics. So here we go. HA and A minus, its conjugate base, are left over. So we know we've created a buffer. It's called buffer. The common ion is called a buffer when it deals with a weak acid and its conjugate base, or a weak base and its conjugate acid. When you have conjugate acid base pairs, it's given that special term, buffer. Okay. All right. So if those are your contents, then you have to write this equilibrium, do a Rice table, use the concentrations you found in step two for your initial row, and then do your change and your final. The nice thing about the common ion, remember, is you can either use the Henderson-Hasselbalch or you can go through the Ka, but really this concentration at equilibrium is just what it was initially, and the salt, the A minus, the common ion from the salt you made in the acid base neutralization, that just becomes the concentration of that. This is the only one that you have to put as X. So it makes the math very simple, but it does make you set up a Rice table. All right, now what if your contents, so from the first drop of base to the equivalence point, between those two, between this point and the equivalence point, you are going to have a buffer. So you're going to have to do this one. But once you've neutralized all the acid and base, and the only thing you have left over is your conjugate base, then you have to set up an equilibrium. A weak base, like you learned in the video yesterday, weak bases can either be amines or they can be conjugate bases of weak acids. And that's what you're going to have in this setup. So your weak base is going to react with water. Water is going to donate the proton, just like Bronsted-Lowry said, and that leaves hydroxide. So this is the equilibrium that you are setting up, but this is specific to the equivalence point of a titration. That is the only time you have to worry about it. Yes, it's going on other places, but we said the pH is determined by the strong, and these Kas are so small compared to the Ka of the weak acid that even though this equilibrium is occurring when this one's occurring, this dominates. We never have to consider it except at the equivalence point. That's when it rises to the foreground and you see, okay, this is going to determine my pH. So only the weak acid, common ion effect buffer, use the weak acid. At the equivalence point, you don't have any weak acid, so you have to let the conjugate base react with water. And that means you're going to have to calculate a KB. So it'll be KW over KA. So don't forget that. So KB for A minus is going to be KW over K of its conjugate, right? These are conjugate acid base pairs. So if you want the K for this base, you have to take KW over its acid. Okay. All right, so then that's just another rice table. And you'll get POH, that's the difference. Here you're going to get hydrogen ion concentration. Here X will equal hydroxide. You'll get a POH, subtract from 14. So this one adds an extra step for you. However, if your contents don't have any of the weak acid and don't have any of the, or it still may have that, but it doesn't have any of the weak acid, then you cannot have a buffer. The buffer had to be both of them at the same time. This is only going to happen, or we're only going to have to worry about it when it's at the equivalence point. But once I have left over strong base, that K is so much larger than this one, you can ignore that reaction and just focus on setting up the POH so I can find directly from moles and volume what the hydroxide is because it's 100% dissociated. And then I get the POH, subtract from 14, I get the pH.